We are looking here at the Fermat's theorem in a very simplified manner based on a request by a viewer. Thank you for joining me. For this video, I am Mr. H. Very generally, look here at the very top of this screen. We have a function. If it is continuous and it is differentiable at point C, there is a local extreme value, and we're talking here about a relative minimum or a relative maximum. It's synonymous with a local minimum or a local maximum, where the C value, the critical value placed with the derivative of the function, will give you a value in terms of 0. You know what that means, a horizontal tangent line. The slope of the tangent line is equal to 0, instantaneous rate of change is equal to 0. If you want to understand the Fermat's theorem in an easy way, you should look at the statements in both the forward and the reverse direction. In one way, you can say this: if there's a horizontal tangent line present at a critical value, then you have a local maximum or a local minimum. That's one direction of looking at it. In another direction, you can look at it in this way: if there is a local maximum or there is a local minimum, then you have a horizontal tangent line present at that point. You see how we're looking at it in both directions? Well, these are generalized statements because in a general manner, Fermat's theorem holds true for many types of functions, but in some situations it does not hold true, so you look at it in a very generalized manner. I can make you understand this in a simplified manner by means of two examples, but anytime you're looking at this theorem, always try to look at it in both the forward and in the reverse direction. If you have a horizontal tangent line at a critical point, then you're thinking about a local extreme value. If you have a local extreme value, then maybe you're thinking about a horizontal tangent line. We'll start here with an example that actually works with regards to the Fermat's theorem. Cosine x, limited domain 0 to 2 pi. Look right here at the first order derivative, which is minus sine x. You take this minus sine x and determine a critical value or set of values by equaling it to 0 and solving for x. Arc sine or inverse sine of 0 gives you values 0, pi, 2 pi. But 0 and 2 pi you can push out because they end up being endpoints. When you're talking about this Fermat's theorem, you're only looking at local extreme values, so you must have points which are regionally located right and left side of that critical point. And this value fits that. Put pi into the original function, you'll get a coordinate pair pi comma minus 1. This right here is your critical value pi. Now you take that first order derivative and you put pi value in it, which is minus sine of pi, and you're getting a value of 0, which is telling you clearly at this critical value, which happens to be a local extreme value, a relative minimum, a local minimum, there's a horizontal tangent line. M equals 0. This right here tells you there's a horizontal tangent line. In this particular case, the Fermat's theorem holds true in both directions. There's a horizontal tangent line over here which is associated with the local extreme value, which is a relative minimum, and there's a relative minimum value here which is associated with a horizontal tangent line. You're seeing this condition, the first order derivative with this critical point and 0. This condition is being seen with a local extreme value, and this right here is an excellent example where both directions of analyzing or reasoning works with the Fermat's theorem. Our exception function is f of x is equal to a cubic function. When you graph the cubic function, you don't have a local minimum or local maximum. If you find the first order derivative, it's going to be 3x squared. You take this first order derivative, equal it to 0 and solve for x, you will get a critical value 0. This here is my critical value 0. You put 0 in the original function, you get a coordinate pair 0, 0, which tells you at 0, 0 you have a critical value and something should be happening at that value. You put this critical value point 0 into your first order derivative, you're getting here a 3 times 0 square. I'm looking at it right here. I'm getting a 0. At this critical point, I'm developing a slope of a tangent line to be 0, but I'm not seeing a local extreme value, a relative minimum or minimum. Here the tangent line is 0, slope is 0, but it cuts across to the function and it does not predict or define a presence of a local extreme value. We have a continuous function, a differentiable function. We end up seeing a slope here of a tangent line to be 0, but we don't see an extreme value, a local extreme value. In this particular case, the Fermat's theorem does not hold true. We have a horizontal tangent line, slope 0, but we don't have a local minimum or local maximum. We just don't see it. So when you're looking at the Fermat's theorem, it is at best a generalization. If you have a local extreme value, you can see a situation such as this, a horizontal tangent line. if you have a horizontal tangent line at a critical point, you are likely to see a local extreme value, but not necessarily as was in this case. Have a good day. Thank you for watching.